Hey everyone. So today I'm going to be demoing how you can enhance the security of your container images with continuous patching. So let's get started. There are many challenges involved in vulnerability management. Some challenges we often encounter include the sheer number of vulnerabilities, how many exist today, and the high frequency in which they appear. Prioritizing which vulnerabilities we need to address first also adds a layer of complexity here. As we see on the graph here, this is a growing problem, and it's only going to increase from here. To effectively mitigate such threats, it is crucial that we prioritize actively exploited vulnerabilities, leverage threat intelligence, and regularly schedule scans to detect new vulnerabilities that may come up. So, in order to deal with these problems, we have a great open source tool called Copacetic, which is currently in CNCF. It patches OS-based vulnerabilities. How it works is that it essentially takes all the packages within an image, updates them, and puts a new patch layer on top. This removes the need to go upstream for a full image rebuild and allows anyone to patch an image when a vulnerability is found. On the slide here, you can see all of the supported operating systems. The next question is, how can I implement this in my daily processes end to end? I'll give you an example of how our team, the Azure Container Registry, is going about this. We have a new feature called continuous patching, which is currently a pilot in private preview. It uses the open source tool Trivy to scan an image and Copacetic to patch it. We provide the functionality for users to specify an image and have these images constantly patched on a customizable schedule. We have two main scenarios here. The first one, image publishers. We have many teams within Microsoft who actually host images for other teams to consume from. With vulnerabilities appearing every day, there's a constant need for these image publishers to maintain the health of their images and to keep their downstream consumers happy. This leads to a bigger maintenance overhead that our feature can help relieve. Second, image consumers. These consumers often rely on upstream publishers and maintainers for patches, new images, and fixes. They also can't control how often upstream images are updated. For example, an upstream maintainer might update the image once a week, every 2 weeks, or once a month. And this schedule may not work for the customer's security benchmarks or SLAs. So for those who have a stricter security mindset or stricter requirements, continuous patching helps to reduce this risk on upstream dependencies for at least OS-based vulnerabilities. This is an example workflow of a typical release journey. And in a few seconds, we're going to be digging deeper into this through a demo. Here we can see how this feature can be used in an end-to-end format. We see an ACR with a few images, a Flask app built from Python, and an Nginx image. These images are currently also populated in an AKS cluster. So here we see the Nginx 1.21 image in our container registry, and we can go ahead and go into our AKS cluster. And over here we can see a running sidecar container with Nginx deployed. Here, let's just highlight that the tag is 1.21. Now we are at ADO, and this essentially showcases a basic release pipeline that we have. We also specify Nginx in our deployment YAML, as you can see on the screen here. So once this is established, we want to scan this image. And so firstly, we just log into our ACR, and I'll be using Trivy as a scanner to see how many vulnerabilities we have today. So we run this command. And wow, okay, so we have 257 vulnerabilities and 21 of them are critical. So we want to set up our continuous patching workflow to see how we can remediate these vulnerabilities. And to do that, we need to set up a short JSON file. What we are asking from the customer here is to specify the repository and tag that they want scanned. We currently support two tagging conventions. The first one is a floating tag, which is simply appending -patch to the image, and the tag will always point to the latest patch. For example, Nginx 1.21 becomes Nginx 1.21-patched. In this case, we're going to be using incremental tagging, which is synonymous with semantic versioning. In semantic versioning, using the Nginx image we have here, it'll turn 1.21 to 1.21-1, -2, -3, etc. So once we fill in all the fields, we can go ahead and save our JSON file and then go back to our terminal to run the supply chain command. As a pilot program, we currently don't have a portal view and rely solely on the CLI. We rely on ACR tasks in the backend, which are essentially native GitHub actions. So now we can see that our supply chain task is running, and we could go check on this in the portal. So here we have 3 ACR tasks running when the workflow is triggered. The first one is the trigger workflow, the second one is the scanning workflow, and the third workflow is the patching workflow. So for the purposes of this video, I'm just speeding it up to see how long the entire workflow takes to run. We also have logs there, as you can see, for easy troubleshooting. So once the workflow is done, we could see here that it took around 30 seconds to trigger the workflow. It took another 30 seconds for Trivy to scan the image, and it took around a minute for the image to be sent to Copacetic and be patched. So all in all, around 2 minutes to run this workflow. Now we can go ahead and we can see that our CSSE policies -patch policy repo was created, which is essentially the JSON configuration that we had made earlier, turned into an OCI artifact and put into the registry. The purpose of this is to keep a source of truth for our working tasks in the back that we can always refer to. And so every time you update the JSON file, the artifact will update automatically. And you can also do this through the CLI. We also want to check that there's a new patched image in the Nginx repository. So once we go into it, we can see that there's a new image 1.21-1 created. And because we selected the incremental tagging option earlier, we can see it's appended with -1. So now let's go ahead and rerun the Trivy scan and see how many vulnerabilities we have left in our image. Okay, so we can see that we have 0 vulnerabilities now. And if you can remember earlier, we had around 257. So this is definitely the best improvement we could have expected. So how do we deploy this image in a more automated fashion? So I'll now show you how Dependabot can play a role in this. Dependabot is a tool that helps manage and update software dependencies automatically. It periodically checks for updates to the dependencies listed in your project's configuration files and creates pull requests to update them. So on the screen here, I'm just running the Dependabot pipeline. It'll bump your image, create a PR for it, go into the deployment YAML, and change the version from 1.21 to 1.21-1. Dependabot typically scans every 24 hours, and the PR will be auto-generated, but for the sake of this demo, I triggered the Dependabot pipeline manually to avoid waiting the 24 hours for the scan. So now we see that our pull request has been created, and we can go ahead and manually approve this PR. So once we've completed the merge, this will trigger the release ADO pipeline. And this pipeline simply installs kubectl and points it towards AKS. So once this deployment is done, we can go ahead to our AKS tab to see if the image has been updated in our sidecar. And now we can see that it has been updated to 1.21-1, which means that our pipeline and our automated flow was successful. This was just a demo and an example of how one can rely on ACR's continuous patching feature and Dependabot to create this end-to-end with the least amount of manual work involved. Thank you.